Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem shuffle integers, and it is a medium level question and it's a problem of the day on Geeks for Geeks. The company tags of this question are Amazon, OYO Rooms as well as Apple, and the topic tags are arrays, recursion, data structures and algorithms. Just to mention, we'll not be using any sort of recursion to solve this question. Like there are methods which uses recursion, but in the case that in the solution that I'm going to explain, we are not going to use recursion. It's definitely an out of box sort of solution. Very few people come up with such solutions. So this solution would be definitely unique, and yes, it's one of those videos that you'll find this. And also, let us go through the question first. So, given an array ARR of n elements in the following format: A1, A2, A3, A4, so on, AN by 2, B1, B2, B3, B4, so on, Bn by 2. The task is to shuffle the array to A1, B1, A2, B2, A3, B3, and so on till An by 2, Bn by 2 without using the extra space. Okay, in place is what they clearly mentioned. Note that n is even. Great, n is even. That means there are going to be n always even elements, because given an array ARR of n elements, so n will also be n. That it's also given that n is even. So always your number of elements would be even. All right, so we'll understand this example more clearly, and expected time complexity is O of n. That's what we are following, and auxiliary space is O of n, and these constraints are the game changers here. Okay, so this is what I've actually used to solve this question. So n goes up to 10 power 5 and array of I goes up to 10 power 3. Great, so these are the things that have been given. Now let us go through the examples now. So here we have array to be 1 to 915. Okay, so if we just divide this into two halves, the required output is all the elements in the second half. Okay, all the elements in the second half must take the odd index positions in the final array, and all the elements in the first half must take the even index positions in the final array. All right, so let us assume the final array is like this. Okay, this is the final array, and now you need to substitute, or you need to put the elements of the first half in the even element index. So what are the first half elements? 1 and 2. So put that. So 1 and 2. And what are the elements in the second half? 9 and 15. Put them in the odd index. So 9 and 15. So that's the reason 1, 9, 2, 15 is the required output. I hope you people understood. Let us do the similar thing here as well in the second example. Divide that into two halves, and now write that array, the final array. And now elements in the first half must be in the odd index positions. What are the elements in the first half? 1, 2, 3. Put them in the odd index positions. So sorry, even index positions. So 1, 2, 3, because this is 0th index, this is second index, and this is 4th index. Okay. And now what are the elements in the second half? 4, 5, 6. Put them in the odd index, odd indexes. So odd indices. So that is 4 and 5 and 6, because this is first index, this is third index, and this is fifth index. Okay. So 1, 2, 5, 1, 4, 2, 5, 3, 6. That is the required output, right? So it matches. So I hope you people understood what are we actually trying to do. So just that we divide that into halves and shuffle those elements accordingly. So what is the logic here? You might find, and just stressing on this fact that you might find various solutions to this question. There might be various other possibilities of doing, like as mentioned in the Geeks for Geeks, this can be solved using recursion, but we are not going to use any of them. We are going to use a particular thing that has been highlighted in the question itself. What is that is, if you carefully observe, the array of I goes up to 10 power 3. Great, array of I goes up to 10 power 3. That means the maximum value that array of I can take is 10 power 3. So let us use that. Okay, so what can we infer from that point? That array of I is less than or equal to 1000. So there will be no element, no element that is greater than 1000, isn't it? There will be no element in the original array that has been given that is more than 1000. That is for sure. So we'll use this property. First, let us deal with the very first example itself. Let us write this here: 1, 2, 9, 15. Okay, so remember the fact that there will be no element in the given array that is greater than 1000. Okay, so what if we modify the elements to be greater than 1000, and what are we going to get from that modification? We can store two elements in that particular position. What am I actually trying to say? So let us consider this position. Okay, let us consider this position. What if I replace 9 with some element that is greater than 1000, so that I can store 9 as well as 1 in that? I can store 9 as well as 1 in that. So how can I do that? So I'll just multiply 1001 with 1. Okay, so 1001, just a number greater than 1000, so 1001 into 1 plus the original number that is there here, 9. So what is this result to? 1010. So I'll be storing 1010 in the position of 9. I'll be replacing 9 with 1010. But how can I get the value of 1 and 9 in this? So 1010, when I divide it by 1001, I would be getting 1, that is at this particular element. And when I do the remainder, a modulo with 1001, I would be getting 9, isn't it? So if I replace this particular element 9 with 1010, I can have 9. I can also even have 1. I can even get 1000 and I can even get 1. I can even get 9 just by doing some operations with 1001, because 1001 is what we have multiplied with 1 and added to 9. So that is what I'm trying to do. In place itself, we are modifying the data. We are using the constraint that has been given. It it has been clearly mentioned that array of I cannot go like more than 1000, it cannot be there. So that is the fact that we are using. What are we trying to do is we are modifying the element that is there, we are multiplying it with 1001 to the elements in the first half, and we are adding it to the particular right half element, and then divided by 1000 we could get the left half element, and modulo 1001 will be getting the right half element. Okay, so that is what we are trying to do. So just apply this formula for everything and try to get it. So 1 to 915 is what if we have taken. So what I'll be doing is the modified array would be, so in the first half we will not be doing any operation, but in the second half this 9 transforms to 9 is transformed to 1001 into 1 plus 9. So this becomes 1010. So 1010. And for 15, this 15, how can we get this 15? 15 will be replaced by 1001 into 2 plus 15. So that is 2070. So how are we going to, what is the other operation that we are going to do? Like this is what the modified array is, modified. But we need to get the final array. The final array is, how are we going to get the final array? So in the final array, this would be 1, and but in this 2 position, this should be replaced. So how are we going to do this? That we'll be using 1010. So 1010. So let us, I'll just erase these two also. So using this particular 1010, how are we going to get these two elements? 1010, when I divide that by, when I divided by 1001, so 1010, I'll just write this, 1010 divided by 1001, I would be getting 1, and 1010 modulo, okay, modulo 1001, I'll be getting 9. So this is what I'll be writing here. I'll be writing 1 and 9. Okay, and now use 2017. So when I use 2017, so 2017 divided by 1001, I'll be getting 2, and 2017 modulo 1001, I'll be getting 15. Okay, so 2 I'll be writing here and 15 I'll be writing here. So 19215 is the answer. So 19215 is the answer. I hope you people understood. So we are modifying the data in place. Great, we are modifying the data in place. So the thing is, we are using the first half elements, we are doing some operation on them, and then we are adding on to that to the second half elements, and we are using the second half element results, final results, to get the like final array elements. Great. So if we do the same thing on second array, like the second example array. So first the array that has been given to us is 1 2 3 4 5 6. Great. So what is the modified array? Modified array looks like this. Modified array looks like this. So first half elements will not be disturbing them, but the second half elements, so 4 will be replaced by 4 plus 1001 into 1. Okay, so that becomes 1005. Okay, so 1005. So 5 is replaced by 5 plus 1001 into 2. So that is 2007. And 6 is replaced by 6 plus 1001 into 3, that is 3009. Okay, 3009. So this is the modified array. And how are we going to get the final array? Final array we are going to get like this. So we'll be using this particular elements in the second half. Okay, so first we'll be using 1005. So from 1005, so 1005, if I divide by 1000, I'll be getting 5, and if I do the modulo with 1000, I'll be getting okay, so this is, sorry, this is not 5, this is 1. So this is 1 and this is 5. So this is what I'll be writing, 1 comma 5. Okay, now I'll be using 2007. So when I use 2007, so 2007 modulo 1001, so sorry, it must be 1. Okay, so modulo 1001, I'll be getting so this particular thing. So this is not 5, this is 4. Sorry for the confusion. Just okay. So this is 1004. This is 4, and so 2007 divided by 1001, I'll be getting 2, and 2007 modulo 1001, I'll be getting 6. Okay, so isn't it, sorry, 5. So I'll be writing these two elements here, 2 comma 5. And now what's the final thing that you are left to use? The 3009. So 3009. So 3009 divided by 1001, I'll be getting 3, and 3009 modulo 1001, I'll be getting 6, right? So I'll be writing those two elements, 3 6. So this is the final array. So this is the final array. If you just see 142536, 142536, it matches. Great. So this is what we are going to use. So the logic is we'll be operating on the first half elements and adding that result on the second half to get the modified array, and we'll be dealing on only the second half elements of the modified array to get the final array elements. Okay. So the same thing, let us put in the code also. So first, what we'll be doing is int m equal to n by 2. So we will be only operating on the halves. Okay. So for int I equal to 0, I into I less than m, I plus plus. So what I'll be doing is array, so nums of I plus m is equal to nums of I into 1001. Okay, 1001. Great. So I hope you people are understanding. That's what we have done. So we are adding. Okay, so I'll just write this plus equal to. So we are adding the first half elements into 1001 to the second half elements. And now what we'll be doing is for int I equal to 0, I less than m, I plus plus, nums of 2 into I. Okay, nums of 2 into I gives the odd is in even index positions 0, 2, 4. Okay, in that position, what are we going to put? We are just going to put nums of I plus m divided by 1000. Okay, and at odd index positions, 32 into I plus 1. So we'll be putting nums of I plus 1 m modulo 1000. Okay, modulo 1000. So it's very evident, right? Because we have multiplied with 1000 the elements, so that's the reason we are dividing them, and modulo gives the thing that was originally there. So that is the second half element, and that's it. So when you run this, you'll be getting that particular answer. So you can verify. So yes, okay, there is some mistake. So int m equal to n by 2, I plus m plus equals to, so I'll just write this properly, nums of I into the, okay, so here the mistake that I have done is I have divided by 1001, so I need to do with 1001, right, not 1000. So whatever the number that we have multiplied, that is what we need to divide and do the modulo. So yes, it works now. So I'll even submit for your reference. Okay. So yes, it worked. I hope you people understood what are we actually trying to do. The same thing we can even do it in bits. Okay, the same thing we can even do it in bits. So instead of plus equal to, we can write or equals to, and nums of I into 1001 can be replaced by left shift of 10. So when we're doing left shift of 10, that is multiplying it with the power of 2, like 2 power 10, right? Left shift of 10 in the sense 2 power of 10. When we are doing 2 power of 10, 2 power of 10 is basically 1024. So it's just basically like multiplying our nums of I with something greater than 1000. So 1024 is also going to work. And now nums of 2I is basically nums of I plus 1 divided by 1001. So this will be replaced by right shift of 10. So we are multiplied with 1024. We must also divide with 1024 to get that element. So dividing with 1024 is basically nothing but right shift 10, right? And nums of I plus 1 module, this is basically n of 1023. Okay, so the simple thing, like if you just put it on the paper, you'll understand. So divided by 1024, for that reason we have done the right shift here, and here nums of I plus 1 and 1023 to get that element that was originally there. Okay, so to that we have did the OR operation, and we have did this, we have got this, right? So now to get that particular element, we'll be doing the AND operation, so that we'll get it. So if I just want, if you want me to do this dry run on this 19215, okay, 19215, so this 2 is being replaced by, so what we'll do is nums of I, this is 1, so 1 left shift of 10, so that is 1 into 2 power 10, so that is 1024, and 1024 if you just represent it with bits, so 1 1 0 0 0 0 0 0, so 2 power 10, right? So 0, this is like this is 1, this is 2, I'll just write it a different thing. This is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64, this is 128. Okay, I'll just write 2 more bits. So this is 256, and this is 512, and this is 1024. Great. So this is 256, this is 524, and this is 1024. Great. And this we are actually doing the OR operation with the original number that we have. So what is the original number we have? That is 0 0 0. I'll write with writing itself 0 0 0 0 0 0 0 0 0 1 0, right? Originally we have 2 here, so with that we are doing an OR operation of with 1024. When we do it, we get 1 0 0 0 0 0 0 0 0 1 0. Now here, if we do the right shift, whatever the right shift, if we're going to do with the 10 digits, we'll be getting this particular thing, isn't it? We'll be getting this. And if we do the AND operation with 1023 in the sense this is 0, everything would be 1, right? Everything would be 1. If we do the AND operation here, only that bit will be getting in the result that is actually there. So if we do the AND operation, we'll be getting 0 0 0 0 0 0 0 0, except here we'll be getting this particular thing. So if I missed anything, 0 0 1 0. So this is basically 2, that is originally present at this particular point. Okay, so when we do this right shift operator, right shift with 10, we'll be getting 1, and that is this particular thing. All right, so with the help of bits also we can solve this. So similarly, you can do the same thing on 15 as well. So it's just that we are first doing the left shift, and then we'll be doing the right shift. Okay, and then we'll be doing the AND operation, because initially we have done the OR operation. So to get that value with what you have done OR operation, you need to do the AND operation, so that you'll be getting the final like the original number that you have used for doing the AND operation. So bits might be confusing at the very first instance, but if you actually solve it using a pen and paper, it will be very much clear. And this particular thing before that, whatever we have used without using bits, that's much more better than this. Like in terms of time space, like time complexity, bits is best, but in terms of understanding, that previous solution that I have written, that is best. Okay, so I hope you people understood. So if not, please go through the video once again. This is very understandable, to be honest. I've explained in the grassroots level everything that is possible. I've explained. In between, I had some hiccups, like I had some wrong calculations, but still I hope I made the concept pretty clear. I hope I made the calculation that we need to do the modified array and final array pretty clear, right? So thank you for watching, guys, and also for your reference, C++, Java, Python code are there in the description. Please go through them. Thank you.